Okay, so I'm Viviane Zwanger, and this is Henning Braun, my colleague. We are both from the Institute, Fraunhofer FKIE, and actually we are giving this talk because we think it's a little bit too risky to keep it to ourselves. So we are sharing it with everybody, so it cannot be used in secret anymore. So yes, this is a talk about bypassing the core isolation memory protection. So this very thing, so yeah, you can see here a screenshot from the control panel. There is the memory integrity. So no, it's not about the core isolation, it's about the memory integrity. And by the way, we Germans, we don't say memory integrity, we say Speicherintegrität der Kernisolierung. And of course, all Germans put this to on. So what's the HVCI memory integrity? As to my knowledge, many people aren't aware of this feature and don't turn it on, and it's also not turned on by default. It's a mechanism relatively new, part of the core isolation, but not enabled per default, in order to protect the kernel, or maybe even more precisely, the kernel memory security, and it also protects the user to a lesser degree. So it uses virtualization-based security, in short VBS. I think this is a Microsoft term. There are hardware requirements. If you've ever seen this little message in the bottom right corner, then this PC doesn't currently meet the minimum system requirements to run Windows 11, then that's exactly about it. So there are hardware requirements that are needed, well, to have the memory integrity running. What is this memory integrity? Microsoft, I guess they were quite annoyed about all the 0 days happening each month. And also there are so many vulnerable, crappy third-party drivers. It's way out of control, and I think Microsoft knows this. And because of that, because they really got, I guess they got sick of the 0 days and vulnerable drivers, so they thought, what can they do to stop or maybe even limit those read-write primitives? And they developed the memory integrity, so actually it exists since Windows 10. And they always threatened to make this a default on Windows 11. But to my knowledge, this hasn't happened yet. So yes, the core isolation is on, but memory integrity is another thing. And no, it's not turned on by default. By the way, maybe you've watched the talk of Yarden Sharif 4 months ago at the HEXACON2023, where she basically tested about 600 or more vulnerable drivers on the LOL drivers repo and found out that 170 or more drivers would just load fine on the latest Windows 11 with latest security stuff and core isolation turned on. Not memory integrity, but core isolation, and that's the important thing because there's the driver blocking list. And as you might know, Microsoft doesn't exactly do a good job of updating it, but maybe Microsoft is also not to blame because there are way too many vulnerable drivers around, and yes, it's just getting out of hands. So from my perspective, a read-write primitive is something that I just have available. I can just pick up some read-write primitive. There's no shortage of that. And if you ever need one, just go to the LOL drivers repo and take one of the 170 or more vulnerable drivers and have your read-write primitive. So with that in mind, some spoilers about the bypass. The spoiler itself doesn't or isn't a read-write primitive itself. It rather takes one and enhances it to make it work again like it was in good old times before memory integrity turned on. In former times, you just had a read-write primitive and you could do your things. For example, you could write on physical memory and there was nobody going to stop you. But with memory integrity turned on, you cannot do this anymore. You cannot write on physical memory because the physical memory isn't real anymore, but I will get to that. So the bypass is taking your read-write primitive and, well, making it like it used to work before memory integrity. You can, again, write on read-only memory and all kind of stuff. The other thing is that our bypass, it doesn't break anything, so we don't go against any security rule and don't break them. Never. We don't break anything, so it's just a bypass, which might be even better because then we can do the stuff without breaking anything. Let's dive a little bit into the core isolation memory integrity. There are two spheres now with the memory integrity. Spheres is also a Microsoft term. So there is the VTL 0 and there's VTL 1. VTL, by the way, means virtual trust level, but it's not that important. VTL 0 is basically your very normal, untrusted operating system. And again, the very threat model is that your operating system is untrusted and that at any time there can happen a 0 day. That's the threat model, or maybe also a vulnerable driver, whatever. And there will be an attacker and it has a read-write primitive and it might try to corrupt your kernel memory. And that should not happen with memory integrity turned on. And that's why there is VTL1. So VTL1 is basically another operating system, a very tiny one, and it has a secure kernel and an isolated user mode. And there are potentially optional plugins like Credential Guard, etc. So if you look at the big picture, then you will see again, by the way, this is a figure from Microsoft Learn, and I found that to be one of the best figures around. It shows everything, especially everything important about our bypass. So yes, again, there is VTL 0 and there is our normal untrusted operating system. This operating system has the programs, the services, and yes, the kernel drivers, but they are untrusted. A 0 day might happen here at any time, and somebody trying to use a read-write primitive to corrupt the kernel and change critical security data. Or load unsigned drivers, for example. So that's what the VTL1 is for. There is now the secure kernel watching over your untrusted operating system and watching every memory access. And that's where we also get to the requirements, to the hardware requirements and SLAT. So basically, it's about memory accesses. Each time there happens a memory access, the secure kernel will be watching us over the shoulder. It's about memory accesses, and whenever the operating system accesses memory, then, well, it looks totally normal for the operating system. So the operating system thinks that it's, well, normal physical memory, and it doesn't see that it's not, but actually, these memory pages aren't real physical pages. In fact, they are guessed physical pages. And using SLAT, second level address translation, they can be translated to real pages, also called system physical pages. Basically, you have now two page table walks. One is the very normal page table walk. You take a virtual address and translate it to a physical address, but this physical address isn't real. It's a guessed physical page. So you need a second page table walk to translate it from the guessed physical page to the real physical page, which is, well, also called a system physical address. That's why it is called second level address translation. Now the whole idea is about VTL watching over our shoulder like Big Brother and watching every memory access, really, literally every memory access. And as you can imagine, that happens all the time. There's all the time some reading and writing and some executing. And this is why this hardware requirement is really needed. So it's really important to have this done in hardware, because otherwise it wouldn't be performant. Okay, so there is this Big Brother watching over the shoulder for every memory access, and it checks them for rule violations. And that might be the point where the audience says, oh, so there are rules now. Because before memory integrity, there were no such rules. I mean, once you had your physical read-write primitive, you would just write on the physical memory, and that's it. But those times are over with memory integrity turned on, of course. And so let's speak about those rules. As said, our bypass never goes against those rules. It is it adheres strictly to those rules. So first rule is, for example, not going against the access rights of a page as stated by the page table entry. For example, if some page is declared as read-only, then you aren't going to write on this page because it's read-only. And remember, there is Big Brother watching over your shoulder, and those physical memory addresses aren't real, they are just guessed physical addresses. The second rule, I personally hate it the most. It's really the worst one. It's about not allocating executable pages anymore, and that's really bad. I mean, nobody can execute or allocate executable pages anymore, literally anybody. Which makes loading of unsigned drivers pretty hard. And then there is the third rule, which is about not modifying the access rights. This was also done quite frequently by rootkit authors. They liked to edit the access rights. For example, they could edit the page table entry and make one read-only declared page to a read-write page, or maybe they changed a read-only page to an executable page, etc., or a user mode page into a kernel mode page, whatever. And those times are over with the memory integrity, at least if you don't have our bypass, that is. So how does that work? I did a little MS Paint drawing. So imagine that some memory access happens, as said, that happens literally all the time. Let's say that it's just a write. So the normal operating system wants to write on some physical address 123.0.0. Let's assume it's a 5. So it wants to write a 5 on 123.0.0.0, and that's when the Big Brother intercepts and checks for rule violations. So as you remember, there is second level address translation, and this physical address isn't a real physical address, it's a guessed physical address. So the secure kernel in VTL1 can now use this second level address translation to translate a guessed physical page into a real physical address. So maybe it would be 555.0.0.0, whatever. And then it would look up into the page table entry and check the access rights, and maybe it's a read-write page. And then it would say, yes, that is okay, you can write this 5 into the real physical RAM. And then a real 5 would land in the physical RAM. On the other side, if this page was declared read-only, then the secure kernel will say, no, this is a read-only page, you are not going to write on this page. And the 5 would not be written on the real physical page. So nothing would happen, no 5 written into the physical memory. And that's it. So you cannot do much against this outer entity because you are just a normal operating system, and there's some outer entity that can translate your so-called physical addresses into the real physical addresses, and you don't have them really. So the situation looks pretty dire for the rootkit authors, which is probably a good thing. And if you ask me, I would say that in the long run, then probably memory integrity will do quite the good stuff. It will protect the kernel and all that. But unfortunately, we think there's like a bypass, which is the content of my talk. So, by the way, we dubbed it Fabius. Most of you might know this as Flounder, perhaps, but again, we Germans, we don't call it Flounder, we call it Fabius. So, Fabius it should be. And I'd like to give you a short little demo what Fabius is able to do even with memory integrity turned on. And that's why I give it over to my colleague and take the micro. So we are gonna change a kernel routine, a kernel security routine, no less, which is, well, it's ruling the code behavior. And yeah. So one word to say is that for this talk, we were not allowed to give a real-world example due to legal reasons. So we came up with our own narrative. So please welcome the protective stuff incorporated driver TM. This is a driver that is supposed to have a vault. This vault is thought to be very, very secure. You can put valuable and sensitive stuff into this vault and it should be safe. Yes, it's a kernel mode driver and with memory integrity turned on, it should be safe, right? But unfortunately, there is a Fabius. So if you reverse engineer the protective stuff incorporated driver TM, then you will find out that it actually implements a function that would allow to dump this secure vault. However, it's not that easy. Only NT authority can dump this vault by this narrative. So actually, it's implemented as an I/O control code. The idea is that a driver can issue some emergency I/O control code to the vault driver and request the vault to be dumped to file. And if you look at this function here in the middle of the I/O control code, dispatch function, then you can see that the first thing this vault driver does is checking the caller. So the vault driver checks if the caller is NT authority or not. And there is this function, is caller allowed to dump the vault. If you look on the right side, you can see this routine. This is the routine, by the way, which we will replace. So we will really replace this routine in the demo. And it's very simple. It's a Boolean routine. And, well, it just checks whether the caller is NT authority or not. And we want to dump the vault as a normal user and not as NT authority. And we can do that. So, yes, this is the routine we want to exchange. Let's first check if the core isolation memory integrity is enabled. Yes, it is. You can see here it's put to on. So maybe, yes, let's just issue some I/O control code to the driver. And as you can see in the code, this should not be allowed because we are a mere user, and as a user, we won't be allowed to dump the vault. So, status access denied. Not exactly the answer I want to hear. So let's do a little magic. And basically, I will explain it afterwards. I just need to get you a little bit curious. And by the way, you can see that we are a user. So the vault driver resolved us to talk.exe with the PID 23 2376. And yes, no way that we are NT authority, and vault driver says we are not allowed to dump the vault. By the way, talk.exe is some little program from our institute. It's really simple. It's on GitHub, completely open source. You could also download it. It can issue arbitrary IO control codes of arbitrary contents to arbitrary drivers. I mean, you can probably guess why we wrote it, but it's not special in any way. And it's a user mode program. No way it should be allowed to dump the vault. Okay, so let's do the bypass with the little magic. And as you can see, there are some kernel mode addresses. So yes, we are using a read-write primitive. As said, just go to the LOL drivers repo, for example, and take one of the 170 more drivers. It will probably, there will be no shortage of that. So we did this little magic, and let's try to talk to the vault driver again now. And let's see if it now dumps the vault. It does. Surprise. So it just changed its behavior. You can see that it doesn't return status access denied, and I'm sorry, the vault isn't that interesting. It doesn't contain much things. It's just an example driver after all. Just imagine there would be lots of security critical data. Now, if we look back at the debug print, then we can see that now, again, the vault driver resolved us to talk.exe, a user mode program. We now have the PID 5716. No way the vault driver could have mistaken us for the NT authority. No way. We are a user mode program, and yet it dumped the vault, and it shouldn't have done this. So the only way we could have get this result is by changing the kernel mode routine, which we did. And well, that's the demo. I will explain this now. Blah. Okay, works. Ja, sonst mach's einfach klein. Kannst du mir geben. Okay, so that was the demo. I hope you're curious now. And as already said, oh damn it. Where's my demo? Here. Okay, so about Fabius. Fabius, as said, it strictly adheres to the rules, to all the rules. It does never break them and still manages to write on those memory pages and still manages to exchange kernel routines. How's that? That's a clear paradox. So something must be wrong. And yes, something is probably wrong. The HVCI memory integrity only ever watches the access rights of pages in order to get some thief violating the access rights. Now you might say, why is that bad? That sounds totally right. If you want to catch somebody going against the access rights, then probably you should be watching the access rights, right? No, it's not, because it's not sufficient, unfortunately. Because the whole model is about an untrusted operating system. And with an untrusted operating system, a 0-day might have happened, or a vulnerable driver loaded, and somebody might have a read-write primitive. In other words, somebody might be able to change the translation system. So the first page table work, translating a virtual address into a physical address. And that opens a real huge space for trickery. So about the technical part, I think we need page table entries. I hope the audience knows what page table entries are, but let's say they are administrative entries that tell about where a virtual address is located in the physical memory, and forget SLAT for a second. And the other thing that is declared on a page table entry are the access rights. But as said, our bypass doesn't go against the access rights. So that's how I would draw a page table entry. The very most important thing probably is the page frame number. The page frame number just tells, well, what it states, the page frame number, meaning that 374, if you just go into the ROM and take the 374th page, then this is your page. And pages are multiples of 1,000 hexadecimal, so if you add 3 zeros to it, then you get the physical address of this page, more or less. So there are also access rights on this page table entry. For example, the user mode and the kernel mode flag. The rootkit authors liked to edit the U into a K or maybe a K into a U, but I think the first case is more common due to obvious reasons. The other thing is that there is a read, write, and execute access rights. Rootkit authors also like to edit those in pre-core isolation memory integrity times. So there is, for example, yeah, you might change it to, well, whatever. Let's just say that the combination of writable and executable together is completely invalid under memory integrity and just totally disallowed. And the other thing is, no, you are not going to edit those access rights with memory integrity turned on. No way. And our bypass doesn't do this either. So let's really start. Things we need is, as already mentioned, your read-write primitive. As a suggestion, there is, well, LOL drivers, or take it from some other place, I don't know. You have a read-write primitive. And you also obviously need a target. As a suggestion, let's say that we have a security critical data page. It's a kernel page, and it's the worst one. It's read-only. And of course, we want to change the data on this read-only page. And yet we can't because the memory integrity is turned on. And Big Brother is watching over our shoulder for every memory access. Yeah, but we have Fabius, so don't fret. We can do something about this. And then there is the last thing we need, and lacking the exact terms of it, I would call it a rogue page. So in this case, we need a read-write page. It doesn't matter where you get it from. You might get it from the beep driver. This has some tradition. So the beep driver has, for example, a data section, and this data section has pages that are read-write. You can borrow them, and I can tell you what, a beep driver will continue to completely to work normally and beep normally. You could also just load the Process Explorer driver, which also has some tradition, and it has lots of read-write pages, so maybe take one of these, or maybe you even allocate one yourself. Doesn't matter, you have a read-write page. So with this, let's edit this security critical page, which is read-only. For this, we just read from the security critical page and copy the bytes to our read-write page. I mean, this is certainly fine because reading from a read-only page is with the rules. Then we start editing the read-write page, which is also okay because it's read-write, so no issues here. We edit all the security variables to our heart's content. I mean, it's just a working copy, so nothing is bad about that. And then, well, then we do the evil thing, and we take the page frame number from our read-write page, and yes, you guess it already, we put it here on the security critical page. And that's it, because now this security critical kernel mode read-only page points to our modified page, and nobody cares about that. And well, just look at it. For VTL0 or your normal untrusted operating system, this is a kernel mode page, read-only with some PFN. Yeah, that's okay. And then there is also VTL1. For VTL1, it's also okay because we read from a read-only page, we write to a read-write page, that's okay. And I guess that if VTL1 resolves this security critical page now, it will probably resolve it to our, I'm actually not completely sure to what it resolves it, but I guess it will resolve it to the read-write page. Whatever it is, it would be okay for VTL1, and yes, so all are happy, and maybe the attacker is happy too, and that's the end of this. So yeah, let's take some more practical example. Again, there might be a global read-only disable security variable. This is just a narrative. No real-world cases here. So yes, disable security variable, and of course this variable is set to false. So security is not disabled. And remember, it's a kernel mode read-only page. No way we should be able to change it, but we can, unfortunately. So first thing, get your read-write page. I suggest borrowing it, but you can also allocate it. Next thing is you copy the content of the read-only page to your read-write page and edit it to your heart's content. That means you change the disable security variable to true. Of course, it's just a working copy, so no. There's no worrying about that. Everything should be fine at this point, but this changes at the third step, because here we take the page frame number from our read-write page with the disable security variable set to true, and we put it on the real read-only page table entry, and at this point, this page will point to our modified bytes. That means that we just change a security critical variable, and formerly it was false, and now it is true. So now is security disabled. Well, and we can do this in pretty much every situation. So we can change read-only pages with security critical data and modify them arbitrarily. In the demo, we did a slightly different thing. We exchanged a kernel mode routine. I personally think it's not that cool like the first example, but for this, well, we still have the second rule that forbids to allocate executable memory, and we don't go against the rules. So yeah, there's so much code in the kernel. We probably can find some replacement routine which we need. So we had this routine is allowed to dump the vault, which returns Boolean, and unfortunately a Boolean false, and we don't want it to be false. We want it to return true. So let's find some kernel routine that returns true. However, certain other things are needed. So in a more general case, you have a kernel routine and you want to change its behavior, yes? So you need to find some replacement routine, and this replacement routine needs to have the same offset. This is because you basically change full pages. You don't exchange single routines like you really exchange those pages by page frame number. So this is why the offsets need to be the same. But I can assure you, you will find some routine that returns a non-zero value and is at the same offset. There's so much code in the kernel. And yes, that's almost it. Maybe this routine also should have not much side effects. Best is a routine that does nothing. Well, and then you just change the page frame numbers and you're already done. And so you end up with a kernel routine replaced, yet it wasn't really replaced. We just messed with the translation system. But functionally, it's equivalent to code modification, and there's also some drawback, and that's that there are other routines on the same page. If they get called at the same moment, they will execute some garbage bytes, and this will lead into a blue screen, which is to be avoided. So if this isn't a scenario that is valid for you, then there are lots of other ways how to use Fabius. For example, you can also edit the read-only exports with Fabius. You can edit the import address tables of drivers as you want with Fabius. For example, if you have some antivirus driver that maybe does a ZW query system information to get, I don't know, a process list, and as an attacker you don't want that the antivirus driver that it gets some process info, then you want to sabotage it. And if you want to sabotage it, well, then just replace this ZW query system info API call by overwriting the address in the import address table and make it something else. For example, iOS VDM version available or something else. It needs to return best a non-zero value because ZW query system info, for example, returns an T status, and T status 0 means success, and you probably want to report to the antivirus driver that it didn't work out with the process list info, and it should do some early exit. Yeah, so yeah, that's it. You can replace also kernel mode routines or change their behavior by multiple ways and make some important security kernel routine that formally return false, make it return true, for example. However, your meanings are still limited to some degree, so let's get to the end. There are some limitations. We cannot do everything with Fabius. There's still no loading of shellcode. There is no loading of unsigned drivers due to this evil second rules. The signed code conduct remains unbroken. The memory integrity is quite a good thing, I can assure you. And yeah, last but not least, we only bypass security laws, so we don't break them. Some final words. Best put the memory integrity to on because it's really cool and it still protects you. So if you turn it off or forget about it, you're basically fish fodder. But if you turn it on, there's only Fabius, and I think this is the least bad case. So best put memory integrity to on. It really protects to a good degree. And we are not able to load unsigned drivers. We are working on it. That's it. I hope you enjoyed the talk. So we will also be here all the day and the next day if you have some questions. Otherwise, thank you for your attention. And I think time is more or less over. So if you have some question, I think I have like 3 minutes.